This is the lecture for lesson 22. This section is all about rational functions, and the first part is going to talk about the asymptotes. So we need to discuss if we have removable discontinuities, talk about local and end behavior of these rational functions, as well as vertical and horizontal asymptotes of these functions. So what's a vertical asymptote? Well, a vertical asymptote of a graph is a vertical line x equals a where the graph tends toward positive or negative infinity as the x inputs approach a. So what that means is you may see your graph like this. As we approach some value a here, your graph is going to approach infinity, be that positive infinity or negative infinity. And that is a vertical asymptote. Meaning a horizontal asymptote means that whatever graph you have, maybe it looks like this, is going to trend to a horizontal line that it's never going to cross. So asymptote, you're not going to cross it. You cannot hit it. It is a value of x that does not make the function true. And in this case, your x is going to approach either positive or negative infinity when your y approaches some value. We're going to do b for this guy. So this one, y approaches positive or negative infinity as x goes to a. And this one is x goes to positive or negative infinity as y goes to b. So here we have a sample graph. And you can see that the asymptotes are going to be drawn as dashed lines. Now we have a vertical asymptote at x equals -3, a vertical asymptote at x equals 1, and we have a horizontal asymptote at y equals 0. Now, the vertical asymptote for y equals 0 only works for these two end pieces. So that's where that vertical asymptote is applying. So what this question is asking, though, is can we fill in the correct value? What are we trending towards, positive or negative infinity? So it says as x approaches -3, and then there's this little symbol here. That means from the right. So if they put a plus sign, it's from the right. If it was like this, -3 with a negative, it's going to say from the left. So what I need to do is I need to find -3. -3 is here. As I approach that value from the right-hand side, well, here's the right of it. So if I follow my graph, as I approach it from the right, where is my graph going? Well, my graph is going up forever and ever towards positive infinity. Here we have another example. We have a horizontal asymptote of y equals 1 and two vertical asymptotes, x equals -2 and x equals 1. So this first question, correct that should say positive 1, says as x approaches 1 from the left, what is happening to the function? So I'm going to find my x value of 1 is this vertical asymptote here. I want to approach it from the left. So left of the line is this side. So where is my graph going? It's going down to negative infinity. The second one says I want to approach -2 from the left. So here's my asymptote of -2. I want to go to the left of that line. That is this part here. And that graph piece is going up to positive infinity. So your only choices are positive or negative infinity, and you just have to look to the left or the right of your asymptote to determine that. Now, we are talking about discontinuities here. A discontinuity means there is a break somehow in your graph. One of those is with a vertical asymptote. The other is called a hole, which could be a removable discontinuity. So we're going to talk about the difference here. We have a removable discontinuity and a non-removable discontinuity. Non-removable is when we are left with vertical asymptotes. So if I were to attempt to factor this, I'm going to be left with pieces on top, pieces on bottom. There's no way to simplify the problem. In a removable, this is going to be a whole. And what's going to happen is when you factor, that value is going to cancel out. So because it cancels, it's called removable. The problem is, though, that it's a hole in the graph. So whatever happens here, there's going to be a hole at that spot, and then it continues along. Because in the original function, at x equals -3, 1, 2, 3, I can't plug that into the original problem because that makes my denominator 0. If it factors out, it creates a hole. If it stays in the denominator as x plus 3, then it's a vertical asymptote. So there's two types. Cancels out, makes it removable. If it stays in the denominator, it is a vertical asymptote. What we're going to do is look at some examples of rational functions and determine if we have vertical asymptotes or removables. If I look at this first one here, I have x over x minus 3. There's no factoring that I can do, and nothing is going to cancel out. So that means this piece in the bottom is going to be left there. And if I solve that, x equals 3 is then going to be a vertical asymptote because it is stuck where it is. There are no removable pieces. There's nothing left in the denominator, nothing canceled out. For number 4, we have x over x squared plus 3. So if I look at this, x squared plus 3 does not cancel, or not factor. So there's no factors, which means there's no removable discontinuities. So to figure out vertical asymptotes, we're going to set the denominator equal to 0. Okay, well, if I do that, I get x squared equals -3. Is it possible to do that if I try to square root? No, that's not going to work out. So there's actually no vertical asymptotes in this one and no removable discontinuities. The last one, we have x over x times x minus 3. So these x's are going to cancel out, meaning that we have a removable at x equals 0, because a factor of x is the value of 0. And then our vertical asymptote is what's going to be left. X minus 3 equals 0, or x equals 3. So we can have one of them, we can have both of them, or we can have neither of them. So vertical asymptotes and removable discontinuities are based on the denominator only and when it equals 0. Looking at the horizontal asymptotes, we have to compare both the power in the numerator and the denominator. And there's going to be 3 choices. The first is the power in the top is less than the power in the bottom. So option 1, if the power in top is smaller than the bottom, you're going to go to 0. So the way I say that is Bobo, bigger on bottom 0. If the powers are the same, what you're going to do is you're always looking at the highest power on top and bottom. They're the same. You're going to just divide their coefficients, and that's going to be your horizontal asymptote. And lastly, if your power is higher on top, we're not going to have a horizontal asymptote. We have what's called an oblique asymptote, and we will discuss that later. Let's take a look at our examples here. We have 15x over 3x squared plus 1. So I'm going to look at my highest powers, top and bottom. I have a bigger power on bottom. So bigger on bottom 0 is my horizontal asymptote. So y equals 0 is my horizontal asymptote. All horizontal asymptotes are in the form y equals a number. So horizontal asymptotes are that. Vertical asymptotes are x equals a number. Number 7, we have the function -3x plus 7 over 5x minus 2. So highest powers, we got negative 3x over 5x. They're the same power. So we're just going to divide negative 3 over 5. Does not simplify. So negative 3/5 is our horizontal asymptote. And then number 8, we have 15x to the third over 3x squared. So in this one, we have a higher on top. When it's bigger on top, we do not have a horizontal asymptote. We have what's called an oblique asymptote. And again, for now, you're just going to say we don't have one. It's oblique. The last part of this section is going to determine our x and y intercepts so that once we have all of our information, we can go ahead and graph these rational functions. So we want to find the x and the y intercepts of rational functions. So the way we're going to do that, an x-intercept is when the numerator equals 0. And the y-intercept, you're going to plug in 0 for x. So if I work with the first one here, if I set the numerator equal to 0, 4x equals 0, and solve for x equals 0 is my intercept. So that means the intercept is 0, 0, meaning that is also the y-intercept here. So watch what happens if I plug in 0. 4 times 0 over 0 squared minus 1. 4 times 0 is 0 over negative 1 is 0. So the x and y-intercept is in fact the same value, 0, 0. Number 2, find the x and y-intercepts of x minus 4 over x squared minus x minus 6. So to find the x-intercept, we're going to set the numerator equal to 0. So if x minus 4 equals 0, and I add 4 to both sides, x equals 4 is the x-intercept. So 4, 0 is my x-intercept. To find the y-intercept, I'm going to plug in 0 for all of my x's. So 0 minus 4 over 0 squared minus 0 minus 6 is just going to leave me with negative 4 over negative 6, which simplifies to 2/3. So the y-intercept is 0, 2/3. And our last one, we have 2 over x squared minus x minus 2. So if I set 2 equal to 0, the numerator equal to 0, that doesn't happen. That can't happen. So there is no x-intercept. There's nothing I can do to cross the x-axis. Everything's either going to be above it or below it. For my y-intercept, if I plug in 0 for x, so 2 over 0 squared minus 0 minus 2 is going to leave 2 over negative 2 or negative 1. So I'm going to cross the y-axis at negative 1. We are going to combine everything we did now to be able to graph these equations. So if I want to graph 4x squared over x squared minus 9. So the numerator equals 0 is the x-intercept. So if I set 4x squared equal to 0, I'm going to get x equals 0. And if x equals 0 on the intercept, that also means that's my y-intercept. So 0, 0, I have my x and y-intercept. The next thing I'm going to do is look for vertical asymptotes. So vertical asymptotes are when the denominator equals 0, looking to see if I can factor anything. So I've got 4x squared over, if I factor that, x plus 3, x minus 3. Now things going to cancel out, so my vertical asymptotes are x equals negative 3 and x equals positive 3. So I'm going to find negative 3 and make my vertical asymptote. I'm going to make positive 3 and make my vertical asymptote. If I look at a horizontal asymptote, we've got highest power, 4x squared over x squared. They're the same power, so if I divide those, I'm just left with 4. Y equals 4, so 1, 2, 3, 4. I'm going to have a horizontal asymptote here. All right, so now what I can do is I'm just going to plug in some values to kind of figure out where my graph is going. And if I'm here, let's see, we could preview do -5 and -4. Let's try -5. So I'm picking something on the left of my vertical asymptote here. So plug in -5, I've got 4 times -5 squared over -5 squared minus 9. So let's see, that's 4 times 25 or 100 over 25 minus 9, 16. So this is about 6.25. So at -5, I'm at 1, 2, 3, 4, 5, 6.25. Okay, which means if I have to make it stay within these asymptotes, it's going to go like this. All right, so now I need something in the middle here. So what I'm going to do is I'm going to plug in -1 and +1 and see where my graph is going. So 4 times -1 squared over -1 squared minus 9. Well, that's 4 times 1 or 4. 1 minus 9 is 8. So 4 over -8 is -1/2. So it looks like I'm going down. Let's plug in +1. 4 times 1 squared over 1 squared minus 9. Oh, that's going to give me the same answer. So it looks like it's going down over here. And little trick is in this, if this one's going above the horizontal asymptote, this one's below the horizontal asymptote, this one's going to be above the horizontal asymptote. So let's plug in +5 and see what happens. 4 times 5 squared over 5 squared minus 9 is going to give me that same 100 over 16 or 6.25. And it's going to look like that. Now, again, you could use a scientific calculator or graphing calculator to plug this in to get a good idea of what the graph looks like. And then this is just the work if you were going to do that by hand. The next equation we are graphing is -2 over x squared minus 1. So if we start with our x and y intercepts, our numerator can never equal 0, so there is no x-intercept. Our denominator, we can plug in 0 for x to get our y-intercept. That gives me -2 over -1, which is 2. So 0, 2 is my y-intercept. And I'm not going to cross the x-axis. Next, doing vertical asymptotes, setting the denominator into factored form is x minus 1 and x plus 1, meaning that my vertical asymptotes are +1 and -1. Next is horizontal asymptotes. So we compare the top, which has no power, to the bottom power, which is squared. So we are bigger on bottom, so it is 0 is the horizontal asymptote. So, which is why we do not have any x-intercepts, because we cannot hit the x-axis. Okay, so let's pick a value at, let's try -2. So we plug that in, we got -2 over -2 squared minus 1. So it's going to be -2 over, let's see, 4 minus 1 is 3. So at -2, we're at 2/3. So -2, we're down here. And if we're down here, we got to stay between the asymptotes. Then it would look like that. And And so we could try, if we want to figure out, generally, if this one's going down, this one is going to go the opposite direction. So this one's going to go up. Because again, we know we have no x-intercept, so we know it can't go down. We know it can't cross the x-axis. It has to go up. And then if we plug in positive 2 on the other side, we're going to get that same answer. We're going to get that reflection over here. Positive 2 squared minus 1 is negative 2 over 3. So this one's going to follow that same pattern over there. And here's our last one. 2x to the fourth over x squared plus 1. So let's work with x and y intercepts. If I make the numerator equal to 0, that's x is 0. So if x is 0, y is 0, their intercept is the origin. Let's check for vertical asymptotes. So vertical asymptotes, let's see, x squared plus 1 equals 0. If I move that over, x squared equals negative 1. That can't ever happen, so we have no vertical asymptotes. We check for horizontal asymptotes, of which, let's see, 2x to the fourth over x squared. So highest power at top, highest power on bottom. We're bigger on top, so we have no horizontal asymptote. So it looks like we're just going to have a few points here. So let's just try -2, -1, 1, and 2. All right, so 2 times -2 to the fourth over -2 squared plus 1. Let's see, that's going to be 2 times 16 all over 4 plus 1, or 5. So 32 over 5 is about 6.4. So let's see, 1, 2, 3, 4, 5, 6.4. Do -1, 2 times -1 to the fourth over -1 squared plus 1. So it's going to be 2 times 1 over 1 plus 1, or 2 over 2, which is 1. And then we know x equals 0 is our root, and it's actually a even root because we've got that there. So this should just reflect on the other side here. And if we double check, if I plug in 1, I'm going to get that same 2 times 1 over 1 plus 1, or 1. So yes, it is reflecting on this side, and I am done. So this one will equal this one here. And that is the end of this section. You can go ahead and do your homework.